Ever catch yourself wondering if there's like this one elegant theory that just explains everything? Like seriously, everything. Gravity, the forces, those quirky particles, the whole universe in a nutshell.
A theory of everything, right?
Yeah, exactly. A theory of everything. Well, buckle up because today we're diving deep, and I mean deep, into Garrett Lisi's world of theoretical physics. And let me tell you, he doesn't hold back.
Oh, no, not at all.
He's using these things, and get this, they're called biquaternions. Ever heard of them?
Biquaternions, yeah.
And then there's this whole triality thing. It's pretty wild.
You can get pretty out there, yeah.
And trust me, I get it. This is some seriously complex stuff, but hey, that's what we're here for, right? We're going to break it all down, and I promise by the end of this deep dive, you'll have all new perspective on just how crazy and maybe even awesome the universe might actually be.
Sounds good to me.
So first things first, we got to decode this jargon. Think of it like this. You're trying to explain how a ball moves, right?
Okay, yeah.
You could use, normal words, or you could use math.
Right.
Quaternions, they're like the super elegant math language.
Instead of just dealing with positions, they handle rotations, like how things move, but in space.
Oh, okay, I'm starting to see it now. So it's less about where something is and more about how it's, like, oriented.
Precisely.
Okay, and then biquaternions, they're like the next level up, right? Like quaternions, but with an extra shot of espresso.
That's a good way to put it. They bring in this concept of boosts, which essentially means changes in velocity, how things speed up or slow down.
So like acceleration and deceleration and all that.
Exactly. And what's fascinating is that physicists were already using these complicated equations to describe these rotations and boosts before biquaternions came along.
Really? So they already had a system, but it was just super clunky?
It wasn't exactly elegant, to say the least. So you can imagine how much simpler and more efficient biquaternions are. It's like finding a brand new shortcut to understand some of the universe's most basic rules.
A shortcut for physics that's kind of awesome, but where does this triality thing fit in? That's the part that really throws me. It sounds kind of mystical, doesn't it? Triality.
A little bit, yeah.
But okay, think about a triangle, right?
Okay.
3 equal sides, totally symmetrical. Triality in physics, it's kind of like that, but on this like massive cosmic scale, it pops up in this idea of 3 generations of fundamental particles.
You've got your electrons, those are the famous ones.
Right, like the Beyonce of particles.
Ah, I like that. And then you have muons and tau particles.
Muons, tau particles. Okay, I'm following.
What's intriguing is that these particles, within each generation, they act almost the same. The only difference is their masses are totally different. It's like having triplets, but one of them is like way heavier than the other two. And physicists, they've been trying to figure out why for ages.
It's like the universe has a favorite child, but we don't know why. So how does Lisi explain this? Is triality the answer?
It's like this. Picture each of these particle generations, those electrons, muons, and tau particles we're talking about, each one existing in its own, well, own version of spacetime.
Whoa, hold on. Separate spacetimes. So, like, are we talking parallel universes here?
That's a pretty good analogy, actually. Think of it like 3 parallel universes, each one home to a different generation of particles.
Okay, I've seen that movie, I think, but how can these particles interact if they're off in their own little universes? That just sounds lonely.
That's the cool part. They're not totally cut off. Lisi suggesting that these separate spacetimes can actually kind of merge or at least interact in ways we haven't quite figured out.
Yeah.
Like imagine those universes just barely touching, just for a moment, letting some of those particles from different generations cross paths.
So like a cosmic fender bender, and that's how these particles get to mingle.
Exactly. And those interactions, they could be the key to those mass differences that we were talking about.
Okay, I can see where you're going with this. So it's like each universe has its own set of rules, and when they bump into each other, those rules, they kind of, I don't know, mix up or something.
Think of it like each spacetime has a unique flavor, and when they mix, the resulting blend creates particles with distinct masses.
Okay, yeah, that makes sense. So we've got biquaternions, this elegant math language that helps us understand motion, right? And then there's triality, possibly connecting those 3 particle generations, maybe even messing with space-time itself. And now we're throwing parallel universes into the mix. This is getting intense.
And the rabbit hole goes even deeper when we bring in something called exceptional Lie groups, specifically E7 and E8.
E7 and E8, those sound intense.
Yeah, they're pretty high-level math concepts, but bear with me. Think of them like giant, really intricate patterns that mathematicians use to describe symmetries.
So like how a snowflake has that perfect symmetry, but way, way more complex.
You got it. And here's where things get really wild. E7 and E8, these complex structures, they naturally include triality.
Whoa, wait a minute. So this triality thing, it's like it's built into these Lie groups from the ground up.
It's like finding the missing piece that completes the puzzle, a pretty strong hint that triality might be a fundamental part of how the universe works. And Lisi thinks that E7 and E8 could be the keys to unlocking a theory of everything.
A theory of everything, all because of some intricate math patterns. I'm trying to wrap my head around that.
It's a lot to take in, I know.
Yeah.
But these exceptional Lie groups suggest there might be even more to the universe than we can currently see.
Okay, now you're just messing with me, right?
I'm serious. We experience the universe in 3 dimensions, plus time. But these groups, they hint at the possibility of higher dimensions, where all the really interesting interactions between particles and forces happen.
Okay, higher dimensions, I officially can't visualize this anymore. So we're talking hidden symmetries, maybe extra dimensions, all this stuff interacting in ways we're just starting to grasp. And at the heart of it all, maybe, just maybe, it's all tied together by this concept of triality. Man, it's almost too much, but in a good way, you know? It's like we're getting a glimpse behind the curtain of reality. But before we get lost in those extra dimensions, let's try to bring this all back down to earth a little, you know? So we started this deep dive with this huge question, right? Like, can one theory really explain everything in the universe?
The ultimate goal of physics.
Totally. And we jumped headfirst into Garrett Lisi's world with all these wild ideas, these biquaternions, and this whole triality concept.
It's some pretty mind-bending stuff when you really think about it.
No kidding. Remember those 3 generations of particles we talked about? Like those almost identical triplets, but with those crazy different masses?
Yeah, it's like one of them hit the cosmic gym and the others, well, not so much.
Exactly. And Lisi's saying triality might be the key to understanding why. Like there's this hidden link between them.
And maybe even a hidden structure within space-time itself.
Right. And then we've got those exceptional Lie groups, E7, E8, those intricate patterns like blueprints for the universe, and they seem to back up this whole triality idea.
It's like the math is pointing us in this direction, saying, hey, look over here, there's something amazing going on.
It's a lot to wrap our heads around, but that's what makes theoretical physics so exciting. You know, we're exploring the edges of what we know, pushing those boundaries.
Absolutely. It's all about asking those big what-if questions, even if they sound a little crazy at first.
Hmm.
And that's what Lisi's doing. He's not afraid to think outside the box.
And that's important, right? I mean, we need those big thinkers to shake things up. But I do have to ask, because I know the physics world can be a tough crowd, is Lisi's theory, is it holding up? What are the other physicists saying?
Well, to be honest, it's still a work in progress.
Yeah, that makes sense. It's all pretty new.
And not everyone in the physics community is totally on board with Lisi's approach, which, that's fine. Science thrives on debate, on putting those ideas through the winger.
It's like that saying, iron sharpens iron.
Exactly. And even if some of Lisi's ideas don't quite pan out, they're still incredibly valuable because they make us confront some of the biggest mysteries in physics.
It's making everyone rethink what we thought we knew.
Right. Why those 3 generations of particles? What is spacetime, really? Is there a way to unify all those forces of the universe? These are questions physicists have been grappling with for ages.
And Lisi's bringing a whole new perspective, new tools, to try and crack the code.
And that's what makes this whole thing so exciting. We're just scratching the surface. Who knows what incredible discoveries are just around the corner?
So what you're saying is the universe might be even weirder and more interconnected than we ever thought possible.
I'd say that's a pretty good bet.
And that's what's so amazing about all of this, right? There's still so much we don't know. There's that mystery, that sense of wonder that keeps us exploring.
It's a universe full of possibilities waiting for us to unlock its secrets. And maybe, just maybe, someone listening to this right now will be the one to make that next big breakthrough.
That's what I love about this. It sparks that curiosity, that desire to understand.
Mm.
So to everyone listening, keep that sense of wonder alive. Keep asking those big questions because you never know what amazing secrets you might uncover.